welcome to the 50th edition of our SPCL Bcast here, and I'm very glad that we could convince Tridao to speak today about exciting deep learning techniques. And now I will give the word to Martin to introduce them more formally.
Tri is an assistant professor at Princeton University and a chief scientist of Together AI. He completed his PhD at Stanford University and is well known for his work on efficiency of ML, such as FlashAttention. Among other things, his work received the Colm 2024 Outstanding Paper Award and ICML 2022 Outstanding Paper Runner-Up Awards. In case of any questions, we will have a Q&A at the end of the call. But please feel free to either raise your hand and we will unmute you, or if you feel a bit shy, put them in the chat and we will read them out. So without further ado, the scene is all yours, Tri.
All right, yeah, thanks, Martin. Hi, everyone, really excited to be here. Thanks for having me. Let me screen, okay. I'm just going to talk about hardware algorithms for sequence modeling. This is sort of at the intersection of machine learning and systems, and there's been tons of exciting progress, especially recently. So this is relatively informal, so I'll share some of the recent advances in this area, and feel free to ask questions throughout the talk. I'll also sometimes pause to see if there are questions. And all right, yeah, let's get started. So just to motivate, we've seen machine learning has been making tons of progress recently. So there were tasks that were considered almost impossible just a couple of years ago that are now routinely solved and accessible to almost everyone. So things like fixing bugs. You can have you can paste a snippet of your code, and ChatGPT will be able to tell you there's a bug in the code. This is why. This is how you fix it. It can now generate art, so images and video. For images, it takes less than a second, and it generates pretty decent result. In other domains, such as biology, for example, the folks at DeepMind has done such an amazing job predicting protein structures with AlphaFold and AlphaFold 2 that now tons of companies are using these tools to accelerate drug design. And most recently, they won the Nobel Prize for this work. So we want to understand what enable these advances, what are some of the outstanding problems, and how do we approach them? So in the last 5 years or so, it's scale that's brought about quality and capabilities. So models gotten about 1,000 times larger in the last 5 years or so, and they're trained on 1,000 times more data. And as a result, they do not only better on existing benchmarks, but they seem to have new capabilities. And so this is amazing. Scale is now more closely tied to advances in machine learning than ever before. And so one core challenge with scale is efficiency, and I'll try to convince you that efficiency is important. So there are two reasons to care about efficiency in my mind. One is more on the practical side, which is efficiency makes it easier to train, deploy, and facilitate research on these models. So we can have right now we might have a lot of large and slow models that do really, really well. Can we get to the point where we have smaller and faster models that do just as well? The other aspect of efficiency that I think may be even more important is that efficiency can unlock new capabilities, such as long context. So maybe 2 years ago, when we asked ChatGPT to write an essay in 4,000 words to describe, for example, the best ice cream flavor, it wasn't able to do so, not because it wasn't smart, simply because it couldn't process anything longer than 4,000 words. But some of the advances that I mentioned have now unlocked these abilities, and now models routinely can process 64K, 100K, or even a million tokens. And these are new capabilities that were enabled through efficiency. So for this talk, I'll focus on one main idea, which is hardware-aware algorithms. So these are algorithms that are designed to take advantage of the hardware that they run on. And I'll illustrate this with two examples. One is FlashAttention, where we use I/O awareness, so we reduce reads and writes to GPU memory to use significant speed up. And the second one is on state space expansion. So I illustrated this with Mamba, where we can expand the recurrent states in SRAM to avoid memory cost, and that leads to very strong sequence model with fast inference, and that can match transformer on language modeling. So we've been very lucky to have lots of folks adopting our research. So for example, FlashAttention is in PyTorch, and folks at OpenAI really liked it, so they implemented it in Triton, and now there are many versions of this in a lot of machine learning training and inference library. So now I'll go into the details. So in the first half of the talk, I'll talk about FlashAttention. In the second half, I'll talk about Mamba. In particular, for FlashAttention, I'll talk about sort of the newest version optimized for H100 or Hopper GPUs. Some of these optimizations are quite interesting, and I'll show you that they matter a ton. So let's get right in. So the motivation, the problem we're trying to solve is to model long sequences. And why do we care about this? One, this can enable new capabilities. As I mentioned, if models can reason over large contexts, they can understand books and plays and code bases. In computer vision, this can close the reality gap. So we've seen that if you can model higher resolution images, this can lead to better and more robust insights. And this can also open up new areas like time series, audio, video, medical imaging, where data is naturally modeled as sequences of millions of steps. And the dominant architecture of transformer is fantastic, but it sometimes has trouble scaling to much longer sequences for these new areas. So if we can make transformer efficient for long sequences, we can unlock these new areas. And so what is the issue with long context, with attention? I would argue that it's mostly an efficiency issue. And I'll illustrate this with an example. So in terms of terminology, context length, we're doing sequence modeling. So context length just means how many other elements in the sequence does the current element interact with. And so why can't we just increase the context length? Turns out that could slow down or completely stop training. So here's an example. This was 2 years ago when we took Megatron LM, which is this library from NVIDIA that was still being used to train tons of large-scale models, and we measure the training efficiency. This is usually measured by teraflops per second. This is just 1B and a 3B model, and with context length 2000, it gets to about 140, 150 teraflops per second on A100. So this is really reasonable. But the moment you increase to context length 8K, the training slow down by 2x or completely stop because you run out of memory. And so this is an efficiency problem, especially with attention. And I'll show that if you can sort of address the efficiency problem, you can train longer context models. So this is an efficient way to scale up models to longer sequences. Okay, so a little background. Maybe most of you are familiar, just so that we're on the same page in terms of terminology, talking about the transformer architecture, which is sort of the workhorse of most of these advances. In the second half, we'll talk about how to maybe go beyond transformer or replace, not necessarily replace them, but for now we'll focus on transformer, which for each, which has a bunch of layers. Usually these get called encoder or decoder blocks. And each block has two main layers, the attention layer and the MLP layer. And I'll focus on the attention layer since that's usually more challenging to scale up in terms of sequence length. So again, just in terms of, so that we're on the same page in terms of terminology. So this is now what attention looks like. As inputs, you have the query, key, and value. And these are shaped n by d, where n is sequence length, and d is the head dimension. So typically a sequence length is quite long, on the order of thousands, and the head dimension is typically quite short, in the order of 64 to 128. And given the query and key, you multiply them together to get some similarity score. Then you apply softmax to get attention probability. Then you multiply with the given value matrix, and you get an output. So this, I'm just describing a single head of attention. And naturally, this scales quadratic in sequence length n, simply because you're computing similarity of every pair of query and key. And so the bottleneck turns out to be memory reads and writes. So in the middle, we have these intermediate tensors that are of size n by n. And if you write them to GPU memory, that already incur a huge cost. By the way, this was how it was routinely done, sort of for 5 years before, for 5 years after Transformer was invented, which was people would just write the similarity score and the attention probability to GPU memory. And that's the biggest cost. It's in moving the bits. It's not so much doing the computation, it's just reading and writing things. So we want to, if we want to address this, we want to understand how does hardware work, how do GPUs work, and once we understand the memory hierarchy of GPUs, we'll be able to figure out how to address this problem. So here I'm showing a diagram of GPU with HBM, which is usually the memory, which this is on the order of 40 to 80 gigabytes. And I'm also drawing the SRAM and compute units. And usually SRAM you think of as a really fast cache that's orders of magnitude smaller, but an order of magnitude faster than HBM. And so the way things work is inputs start out in HBM, and then it get transferred to the compute unit and SRAM to do any kind of computation. So it is this slow data transfer. And then after you're done, the output is written back to HBM. And so because of this memory hierarchy, we can exploit this to get speed up. And if we design the algorithm to be IO aware, that is accounting for the read and write to different levels of memory. And so actually we use some of the very, very old and standard tricks in systems, things like tiling and so on. And ultimately it boils down to computing by blocks. So this was how people have been implementing matrix multiplication since the 1970s. But there's some challenges. So if we tile or we compute by block, there's this softmax that requires sort of the full row to do the softmax. And if you want to compute the gradient in the backward pass, you might need the value from the forward pass, like these big intermediate tensors to compute the gradient. And so we address that with some classical techniques such as tiling, that we need to restructure the algorithm and sort of mathematically reformulated it to deal with blocks. And for the backward pass, we can easily recompute instead of store the attention matrix from the forward pass, and this works quite well. That's a sort of the background, and since then FlashAttention has become pretty widely used. But in the last 2 years or so, H100 or Hopper GPUs have come to dominate sort of the fraction of flops in the world. And most large models are trained on H100. They're done on the inference done on H100 as well. And FlashAttention 2 didn't work too well on these newer GPUs. So FlashAttention 2 was already four times or so faster than baseline. But on an H100, where I'm measuring the speed, it's a teraflops per second. H100 theoretical max is about 1,000 teraflops per second. And here I'm showing FlashAttention 2 getting to about 35 or 40% of the theoretical max. And so that's the challenge. We want to figure out how we can go further, sort of designing the algorithm to take advantage of the new hardware. So that's the problem we're trying to solve. Okay. So this is so I'll talk about some of the techniques here. This is joint work with actually led by Jay and Ganesh from Kofax, and we collaborated with Ying from Meta, Vijay, and Pradeep from NVIDIA. So what are the new features of H100? One is this warp group MMA. MMA stands for matrix multiply accumulate, where there's this new instruction that has higher throughput. So that's one. The other one is called TMA, tensor memory acceleration, which provides faster loading from global memory to memory. And this is important to save registers. So these are new instructions that we want to be using. The sort of the main change in terms of software, in terms of algorithm, is asynchrony. And this means that we want to overlap the matrix multiplication and the softmax steps. And I'll show why this is important, that you want to overlap these two things. And it sort of leverage a bunch of asynchronous features from the H100, which more and more accelerators are now starting to adopt. And I'll show two examples of how we can overlap the gem, the matrix multiplication, and the softmax. And then the third thing is low precision. So for a while, it's been pretty standard to use 16-bit, so BF16 to represent floating point numbers. More recently, FP8 has become pretty viable. But of course, it's faster, but of course it trades off in terms of numerical accuracy. So we had to use some techniques to reduce numerical error while getting speed up. So the upshot of this is that after doing this on the same hardware, so if you run FlashAttention 2 on H100 versus FlashAttention 3 on H100, you'll see a 1.6 to 3x difference. So this is pretty exciting. We thought FlashAttention 2 was already quite optimized, but turns out there's quite a bit of head. And with FlashAttention 3, we're pretty close to optimal on this generation of hardware. Okay, so I'll talk about some of these new instructions briefly. So this new instruction, warp group MMA, is a way to use tensor cores to do matrix multiply. And if it's necessary to use these instructions, because if you use sort of the old instruction from a previous generation, like Ampere, like A100, it would still run, but it won't get you maximum throughput. So you want to be using this new instruction. And the TMA is sort of a specialized hardware unit that does the memory copy from global memory to shared memory. And this is important because it saves you time and registers. So instead of having to spend time calculating the indices and padding and so on, there's just a hardware unit that does that for you automatically. And this is important because you want to spend most of your time doing matrix multiplication. The reason is FLOPs on the GPU is matrix multiplication FLOP. GPU is actually now quite specialized, and matrix multiplication FLOPs accounts for maybe 95% of the total FLOPs. So if you don't use the matrix multiply, anytime the tensor cores or matrix multiply unit that is idle is essentially you're not using 95% of the GPU. So you want to spend as much time as possible doing matrix multiply and as little time as possible doing anything else, like calculating indices to load memory from global memory to shared memory. So as long as you use these instructions, you would get pretty decent performance already, but you can do quite a bit better by overlapping the matrix multiply and the softmax. So why is overlapping necessary? or not necessary. Why is overlapping a good idea? A good idea now. It's because the matrix multiply has gotten so fast. This is Amdahl's law, which is that the part that is speed up, the overall speed up is limited by sort of the fraction of the time that you're running this optimized routine. So maybe the matrix multiply, the tensor core has gotten so fast, but any program, the overall speed up is still limited by how much time you spend doing some other things like index calculation or softmax. So just as an illustration, if we calculate, I won't go through all the nitty gritty detail, but this is one block of attention of size 128 by 194. Turns out you do a massive amount of flops in terms of matrix multiply, and that could take 3,000 cycles. But just the exponential in the softmax, only on the order of thousands of operations, because they have much lower throughputs. Because you have much lower throughput, the exponential takes maybe half the time compared to the matrix multiply. This is a pretty big difference. And this is the surprising thing we found out with Hopper, is that the matrix multiply gets so fast that everything else becomes a bottleneck. So, for example, the exponential can take 50% of the cycles of matrix multiply. And for FP8, it gets worse than there. The matrix multiply takes about the same time as the exponential, because the matrix multiply gets twice as fast, but the exponential doesn't get any quite as fast. So the way out is to do matrix multiply. Tensor core, the exponential unit is calculating exponential. So how do we do this? So there are two ideas that we show can work. One is we call inter-warp group overlapping. So the easiest way to overlap these things is to not do anything at all. So if you leave it, but we can do quite a bit better. So here's an example of how you can overlap these operations. So a warp group is 128 threads. So they usually work together to do matrix multiply. And usually for this case, we would use 2 warp groups per thread block. So per SM, we have 2 warp groups. And we want warp group 1 to be doing gem first, to do matrix multiply first. And then as the warp group 1 does move to do the softmax, we want warp group 2 to be doing the matrix multiply. So I'm drawing out the diagram in terms of tab. So the point here is we want to sort of use synchronization barriers between the 2 warp groups, so that while one warp group is doing matrix multiply, the other warp group is doing softmax, and then they switch role. And then they switch role so that one warp group is doing the softmax while the other one is doing matrix multiply. So this is called ping pong scheduling, because you sort of switch the role of two warp groups. And you can go from, for example, 580 teraflops, which is pretty reasonable, to 640 teraflops using this. So that's one way to overlap. The second way you can overlap is even within one warp group. You can have even more fine-grained overlapping between gem and softmax. So in attention, there are 2 gems. There is the times k, that's a gem, and then after the softmax, you take the attention probability to multiply by v. That's the second gem. So what we can do is even within one warp group, here I'm showing the 2 gems, sort of the timeline of 2 gems. So gem 0, softmax, and gem 1. We can schedule the instruction in such a way that so first the number here is the number of iterations. So we first do the gem 0, the first gem of the first iteration. Then once that's done, you can call sort of you can issue the instructions for the softmax while doing the Gem 0 for the next iteration. So this is sort of overlapping pipelining between iterations. Then once the softmax is finished, then you can do the Gem 1 for the first iteration, and then move on to do Gem 0 of the next iteration while doing softmax. So you can issue instructions in such a way that even within one core group, there's some overlapping between softmax and the two gem. So this can work reasonably well. We can get from 640 teraflops to 670 teraflops. There's some trade-off. It does use more registers to sort of store intermediate results, but generally we find this pretty useful. And last but not least, we want to be using FP8, at least for some of the cases like inference. Because with FP8, we doubled the matrix multiplied throughput, but we do have to trade off accuracy. So we need to figure out some algorithmic change to address this. So in language models, we usually run into this issue called outlier features, where I'm drawing sort of the activation magnitude of I think this is llama 3 or llama 2. It doesn't really matter. Most models will have this issue where some of the activations get very, very large, and most of the activations are relatively small. So if you quantize naively, you incur a lot of quantization error. And so one way to deal with this, and this technique has actually been around for a while from the quantization literature, is that you can take a random orthogonal matrix M, and then before quantization, you sort of rotate Q and K by M. So if you take Q, the query, you multiply by M, and then you quantize, and do the same for K. So the idea is, because M is orthogonal, rotating will both Q and K preserve the dot product, so it doesn't change the output. But when you quantize, the features of Q times M is sort of a weighted average, an average of a bunch of features from Q. So if the original features from Q have outliers, after you rotate them, they're more spread out, and you get much less quantization error. In practice, we use a Hadamard transform for this. Instead of any random orthogonal matrix, we use a Hadamard transform multiplied by a random diagonal matrix. The reason we use Hadamard transform is that this is fast to perform. It's done your D log D, where D is the head dimension instead of D squared. And it can be fused with previous operations like rotary embedding almost for free. Okay, so how well do these techniques work? So this work actually quite well. On the same device, we see 1.6 to 2x speedup compared to FlashAttention 2. So this is showing attention speed in the forward pass in terms of teraflops per second, and just changing different sequence length. On the left, this is without causal mask, and on the right is with causal mask. And I'm comparing to either the blue one is the standard implementation from PyTorch. The orange is FlashAttention. Green is Triton, which has started to use some of the new instructions already, like WGMMA and TMA. The red one is cuDNN, which is actually a really good implementation of sort of the same algorithm from NVIDIA. So this is, there's a team at NVIDIA just been working on this for a while. It's actually really good, and they use some of the same techniques that we've used. We more recently, after the paper is out, the code is out, we've been talking to them, and they've been incorporating some of our techniques. So this is actually the latest version of cuDNN just released this month. So it has cuDNN itself has now incorporated a bunch of the techniques that I'm talking about in FlashAttention 3. So generally, we see that cuDNN and FlashAttention 3 are quite a bit faster than some of the other implementations. even though, for example, Triton does use the new instructions, they haven't used some of the sort of asynchrony techniques like overlapping between gem and softmax. So this is on sort of the popular head dimension 128, and so we get to maybe 75% of the theoretical max. And just for context, this is about, if you do matrix multiplication, which is arguably the most optimized operation on the planet, you get to around the same efficiency, around 700 teraflops per second or so on the H100. So now this means that our primitives, we have really, really powerful primitives, like not just matrix multiplication. Normally we think of matrix multiplication as sort of, really, really optimized, and the rest are not so much. Turns out right now with attention, it's about as efficient of a primitive as matrix multiply. So that's amazing. So if we go to head dimension 256, you can get to 850 teraflops. So this is pretty crazy. This is now sort of faster than matrix multiply from cuBLAS, and we reach 85% of the theoretical max, which is usually as high as it goes because it starts to get power throttle. And yeah, actually, I think if the GPU is not power throttle, we reach pretty much close to the theoretical max. But because of power throttle, it gets to 850. So this is amazing. This is on BF16. For FP8, this also works quite well. FP8, the theoretical max is 2,000 teraflops or 2 petaflops. We can reach up to about 1,300 teraflops. This is really exciting because this is like one card getting more than a petaflops of compute. Just I think a couple of years ago this was unthinkable, but now we have just one card doing petaflops of compute, and we have the software to actually take advantage of these cards. So to summarize, FlashAttention 3, this is a fast and accurate attention and optimized for modern hardware. The two key ideas are asynchrony and low precision. And the upshot is you can get faster training and better models with longer sequences. So that's the first half of the talk, focusing on transformer and how to make that faster. And the second half, I'll talk about Mamba, which is this newer class of model based on state space model. And this is joint work with Albert Gu, who's at CMU. So as I mentioned already, deep sequence model, a workhorse of modern deep learning, text, audio, images, and so on. They're backbone of these modern foundation models. And the key concept, sort of conceptually, how we think about the trade-off between different models is that they just have different ways of storing the autoregressive state. So what does that mean? Every autoregressive model, autoregressive just means you use the past information to predict the future, is that they store or they remember some information from the previous time steps to predict the next time step. So that's what we call a state, is whatever the model needs to remember to predict the next step. And RNNs, which were popular back in 2016 or so, before transformers came out, they have a very natural sort of formulation that is autoregressive. So here there's a hidden state HT, and it is a function of the previous hidden state t minus 1, as well as the current input x of t. State space model is actually an instance of that, where the updates rules are even simpler. So these are, you can think of as linear RNN. There's some subtlety here, but I'll talk about later, which is the size of the hidden state. Which is that there is this, we sort of do a blow up. So we think of the input as 1D, and then we blow up to some factor, we call it n, before projecting down to 1D. So now if you have input of on the order of 1,000 channels or so, then you should replicate this 1,000 times. So this is a feature we call state expansion, where the size of the state is n times the size of the input. N is usually on the order of 100 to 10 to 100. And this is helpful, as I'll show later. So state space models, the trade-off is they can be efficient in terms of constant time inference and linear time training. But in the past, they didn't do as well on information dense modalities like language. Whereas with transformer, they do really well on, they have this dense connection, and they do really well on language. They've been state of the art for a while. But the trade-off is they're inefficient, so they generally require linear time inference and quadratic time training. So to make SSM work for language, there are three key ingredients. One is the state size. I sort of alluded to this already. The larger the state size, the more the model can remember information from the past. So as I mentioned, we use this technique called state expansion, where we treat the input, we sort of blow up the input to go from 1D to ND for each of the channel. So that gives you more memory for the model to store the information. The second one is the state update should be reasonably expressive. So classical RNNs like LSTM and GRUs, they use more sophisticated updates that are nonlinear. Here, for SSM, normally these ABC are parameters, but instead the sort of our insight is that if you make these things dependent on the input, they can be a lot more expressive, because they can decide, the model can decide how much of the input should it commit to memory. And this is sort of the main difference in terms of modeling between previous state space and state space models and Mamba. And the last one is that you want these things to be efficient. Can you compute the forward backward pass reasonably fast during training? And the answer is, if the updates are linear, then you can use associate scan, and it's parallelizable. So how do you do that sufficiently? Sort of using the same ideas as before. In FlashAttention, we're going to store some tensors only in GPU SRAM, and we don't write them down to HBM. So here I'm illustrating in green what is stored in HBMs is usually the input and the parameters, ABC, as well as the output. But the hidden state, as I mentioned, we do the state expansion. The hidden state is actually usually quite a lot larger. And the nice thing is we can, during computation, we keep them only in SRAM, which is really fast memory, and never write them down to HBM. And that, again, we exploit this memory hierarchy to make state space, these new classes of state space a lot more efficient. Since then, we've sort of reformulated the algorithm using some fun sort of linear algebra. I won't go into details with Mamba-2. And the idea here is, instead of using scan, we can use specialized units. We can reformulate it to use matrix multiplication, block matrix multiplication. Again, this is using tensor cores. Tensor cores account for 95% of the FLOPs, so we should be using tensor cores. So with Mamba-2, this is sort of the right direction. And since then, there's been a resurgence of these models, RedNet, XLSTM, test time training, and a bunch of others. And they all work pretty similarly. So there's this really nice table from a paper from Salin called DeltaNet that sort of lists out the recurrence of a bunch of these models. So this is a great paper. I recommend it. And most of these models, state space or linear RNN or linear attention, now work pretty similarly. So in terms of state update, they're slightly different, but they don't really change the performance that much. So since we released Mamba a year ago, we've been really excited to see lots of people using this on a bunch of areas like vision, time series, graph, robotics, and so on. And it seems like it's a pretty strong out-of-the-box model architecture for a lot of modalities, not just language. And since then, people have been taking this architecture or this layer and incorporate some other layers to scale up. So folks from Microsoft, NVIDIA, Mistral, CII's Zephyr AS21 have been using this stuff. there's some related models from Google and Cartesia, and it's now it's a new architecture and took some effort, but it's now reasonably supported on Hugging Face, Tensor RTLM, VLM, and on not just NVIDIA chips, but AMD and AWS Trainium and inferential chips. So this has been sort of a year of progress that we're really happy about. So there, attention is great, and Mamba, even though it made significant advances, combining the two seems to do better. So this is what we call hybrid models. So this is a collaboration with NVIDIA where they sort of try to do as fair comparison as possible between different model architectures, Transformer, Mamba-2, and Mamba-2 hybrid, and they saw that this is 8B model trained to 3.5 trillion tokens, that usually hybrid models perform quite a bit better than Transformer. So this is MMRU, the hybrid model is in blue, and the Transformer is in orange. Similarly, AI21 used the Mamba layer in their largest model, Jamba 1.5, which is I think about 400 billion parameters, and they see significant reduction in pre-fill time. So it's 2.5x for the sort of the same quality for long context. Because of TAM, I won't go into this, but it turns out you can also distill a strong pre-trained transformer like Llama to change the architecture into Mamba. Okay, so I'll end with some open questions, how we're thinking about this. On the modeling side, we still don't know why hybrid models do well, or at least I personally don't know, and I'm really curious about this. We have compression in the model in Mamba. Is it a bug or a feature? Because compression does mean that the model doesn't memorize, it doesn't remember exactly what it has seen. It sort of has to compress that information. So that could be a bug, that could be a feature. And ultimately, how do we do adaptive compute? So there's still a lot of redundancy in the input. If you think about, for example, audio or video, most of the frames are not that useful. So how do we adapt the amount of compute to the level of information that the input provides? On the ecosystem and algorithm side, I think there's still a bunch to figure out on how to do distributed training with these new model architectures, how to do efficient inference. We made some progress, but there's still sort of this big ecosystem built around transformers. And again, I'm excited about optimizing for modern hardware. Blackwell GPUs are coming for TPU and mobile chips and so on. And I'll just leave with one last thought, which is how do we get more intelligence per FLOPs? So by intelligence, I mean model capability. So model is just a way to convert FLOPs, which compute and data, into capabilities. And different model architectures are just different ways of doing this conversion. So how do we design a model to use as compute wisely? So the summary is Mamba, it can match the B's strongest transformer architecture and language. The two key ideas, the selection mechanism and the hardware-aware state expansion. And you can get a better model with linear instead of quadratic scaling and sequence length. And with that, I'll stop here. Thank you for your attention, and I'll be happy to take questions.
So thank you a lot for the amazing talk. I will take the moment right now to make an advertisement for the BCast happening in 2 weeks. On the 31st of October, we will have Nicholas Fraser from AMD, and he'll be talking about Brevitas, which is a PyTorch library for neural network quantization. So now we move to the Q&A session. You can either raise your hand and I'll unmute you, or you can write your questions in the chat and I'll repeat them. Okay.
All right. Hi, so thank you very much for your talk. It's very interesting. I have a question about the first part of it, so about the FlashAttention.
Yeah.
So a lot of the improvements that you made in FlashAttention in 2 and then 3, they are, let's say, more on the high-level scheduling decisions, and yet the source code of FlashAttention is using CUDA and Cutlass. and you're not using something like Triton. So my question is, what do you think is mostly missing from those kind of compilers, DSLs, or these kind of languages that help raise these sort of decisions right now?
Right. Yeah. In Triton, I love Triton, and I think it's sort of the best bang for buck if you want. You can get 80% of the way there with spending 20% of the effort. So Triton is amazing, and it's still developing. I think Triton, did make an opinionated decision, which was to abstract things away, right? Abstract. They give you access to sort of a block of elements, but they don't give you access to sort of individual elements and so on. And compilers sort of takes care of that. So that does simplify things, but that does leave necessarily when you abstract things, you make it harder to do certain kinds of special optimization. So for example, I think Triton is very much built by thinking about the programming model on Ampere, where it's a little more sequential. With Hopper, it's more asynchronous, and that's a little bit harder for Triton to do. So doing all sort of this sort of ping pong scheduling, sort of synchronizing two warp groups is a little bit harder to do in Triton. So you have two options. One is you sort of rewrite the compiler to figure out these things, because you already abstract it away, so the user can't use it. So one option is you rewrite a compiler to do some of this stuff for you, or you have to invent new abstractions so that people can use this stuff in a sort of higher level language. So far the Triton folks are working on this, but it's a bit more on the like let's rewrite the compiler so that the users don't have to change their code. I think there's some newer efforts, for example, from Google. The one is called Mosaic GPU, which is also in Python, slightly lower level than Triton, where they expose a little bit more so that, for example, users can write explicit sort of synchronization. So I think there's sort of different levels of abstractions that different libraries are providing. Yeah, maybe that's just necessary, sort of like using the right tools for the job, which is for most of the code that you run, like it can be written in Triton. Torch compiler is amazing, and it's essentially just generates Triton code, and it does amazingly for most of the operations. So most time Triton suffice, but some of the time you might need a little bit more control, so you might reach for a different tool.
All right, great, thank you.
Yeah.
Hi, thank you also for the very nice talk. And I have a question that I think sort of builds on what Tal was just asking, also on FlashAttention, where a lot of the performance that you've been getting, especially with FlashAttention 3, has really come from exploiting very hardware-specific features like the asynchrony and some of the new Tensor Core operations. How much hope do you think there is for automatically porting this sort of level of optimization to other hardware architectures? Do you think this could be automated or automated most of the way, or do you think getting this sort of performance on new hardware is going to require some very low-level performance engineers who are very familiar with the specific hardware that you're optimizing for?
Right. Yeah, this is a great question. Yeah, I think for most of the operations, that's written in a maybe slightly higher level language like Triton. Porting is not so bad. Actually, one pitch from Triton is that it's a higher level thing. You write in Triton, and then the compiler can sort of generate code for NVIDIA GPUs, AMD GPUs, Intel CPU, et cetera, right? And that's great for most operations. There will be a few operations that people care about the performance so much. For example, matrix multiplication, where AMD has a team that's just gonna write matrix multiplication that's specialized to their chips. Like every generation of chip, they're going to rewrite the thing. So did NVIDIA. Like every generation, every 2 years, they rewrite these matrix multiplication. And attention, I think, has gotten to the point where attention is important enough that people are willing to sort of rewrite their code. Of course, for a user, if you're using PyTorch, then it's same old PyTorch and it should work. But PyTorch is now calling a different kernel. With Blackwell coming, I think there's going to be another generation of sort of people rewriting code. So why are people willing to do this every 2 years or so? I think it's because the hardware is changing fast enough that it's providing enough benefits, like a 2x, 3x, usually on your 2x of every generation, that is worth rewriting. And two, the hardware is changing in a way that is like doing more specialization, is giving new features. Unlike, for example, for a while the hardware was changing, which is like just more SMs, more streaming multiprocessor, higher clock speed, and so your old code would run just as well as the on the new device, and you get the benefits for free. I think those days are probably behind us, where now we've gotten to the point where to squeeze out more performance, you got to be more creative, like lower precision, more asynchrony, and so on. So the answer, I think, is for some of the operations like matrix multiplication and attention, people are willing to sort of rewrite every generation. For some other operations that are less performance critical, you can write in a higher level language and hopefully have the compiler sort of generate the new code for you automatically. But of course, you're shifting the code, the work to the compiler writer. So I think there is that tension there of how much you rewrite versus how sort of perform critical it is.
Thanks.
So hello, Chai. So I have a question about the FP8 FlashAttention. So you mentioned that you did the incoherent processing to improve the accuracy. So I have a question, like if you do an end-to-end training run with either FP8 FlashAttention and BF16 FlashAttention, how would the loss converge in terms of the training tokens and also the wall clock time?
Yeah. FP8. So the answer is we haven't done that. So we've only sort of implemented the forward pass in FP8, and the primary use case for that is for inference. I think NVIDIA has written sort of both of FP8 forward pass and FP8 backward pass. I think it's still unclear if that is accurate enough for training. So I think the way they do FP8 is without this incoherent thing, it's just tensor-wise scaling with delay scaling. So I think it's this is what I want to explore next, which is using some of these techniques like incoherent processing. Can we actually get stable training in FP8? In terms of speed, you're not going to get 2x. I think optimistically you can maybe get 1.5x because the matrix multiplications are like 1.8x faster, and then you still have a bunch of operations that are not matrix multiplication, that are in BF16. So I think optimistically we can get maybe 1.5x with stable scaling. I think as a community we will figure out FP8 training in the next year or so as more and more people have access to H100. Not just the Frontier lab, but more and more people will be able to use H100s, and then FP8 training becomes more of an in-demand feature that people will figure out. Right now, still, NVIDIA provides transformer engine. Some people use it, some people don't. I've know some labs that use it, that say, hey, at the beginning, it's match the quality of a FP8 will match the quality of BF16, but if you train for longer and longer, they start to not match it. So I think it's still an open problem how to make FP8 training work reliably.
Thank you.
All right, thank you for the nice talk. My name is Imanol. I'm a research scientist at the AI Center, and I have actually one of the works I did during my PhD was the DeltaNet that you also mentioned that Song Lin made more efficient by reformulating it. I have a question because on Mamba, something that I found a bit puzzling is the state expansion. I mean, I do understand why you're doing it, like the hardware reason for it. But in some of our experiments, we found that just doing state expansion naively. So for example, if you say we diagonalize A, or we represent A as this outer product between like a delta and like another vector, then if you do this naively, it doesn't seem to actually really work. Performance of the model does not increase. So without going into details, maybe you have some thoughts or comments about why state expansion might make sense, structurally instead of just because of the hardware.
Right. Yeah. So I think from a modeling perspective, I think state expansion by itself doesn't work that well. So we've seen that with sort of older state space model like S4, where it still didn't do well on language. So I think that my intuition is that even with state expansion, the size of the states is not that big, right? You're processing input sequence of length, let's say 2000, and at each location, even with state expansion, is equivalent to storing information is enough to store information from like 10 to 100 tokens, right? So if you without a sort of strong state update, an expressive state update, then state expansion essentially amounts to, hey, you can now store information equivalent to 100 tokens instead of 1 token, which is helpful but not enough. For the state update, I think the moment you make these state updates or input dependent, or with DeltaNet, you make these more expressive, and the model can sort of select, which information to put in memory. It's sort of the analogy is as you read through like an article or a paper, your brain sort of picks out what are the important facts from the paper to commit to memory. Or with DeltaNet, you sort of like, in some sense, update the memory that previously corresponds to this piece of information. So I think you also need that expressiveness. So you want to combine the state update, an expressive state update, with a large enough state size, so that one, the model can decide what to put in the memory, and two, it has sort of enough memory to store important information. So once you have these two things, I think in our experience, we've seen that increasing the state size the model tend to do better. And the more sort of expressive state updates also make the model do better. But you sort of need both, I think.
Thank you. Maybe a quick follow-up question. You do mention also adaptive compute as something quite important, and I would completely agree with you. We've seen a few different approaches, like adaptive computation time or like mixture of depths. Do you have like a particular favorite that you like specifically, or even like a completely different direction to the methods we know so far?
Yeah, so I think this is more of a general direction rather than, I don't know the right answer, but it feels like in the next couple of years or so we'll figure out, and I think it's for two reasons. One is that as we expand to more modalities, so for a while we mostly care about text, but now people care about a lot more, multimodal, new modalities like audio and video, where there's sort of adaptive compute makes a whole lot more sense. So in the next couple of years or so, I expect people to figure this out. And the other aspect is why I think adaptive compute is going to be important is that so far we focus on hardware efficiency, but the information in the world has a lot of redundancy. You know, processing an entire video, you're dealing with so many pixels, and most of them are not useful. So for a while, I think we're in the phase of like, let's just scale and figure out if it works at all. You know, sort of throwing compute at the problem, and we've seen it works amazingly well. But the next phase will be, can we actually make it efficient? Can we actually sort of get more intelligence per flop? So that's where people will care a lot more about sort of the efficiency and the how to reduce compute for tokens or for pixels or for frames that are not as important. Right now, sort of my pet project is to not have to deal with tokenizers or doing the character level modeling, and you know, whether the model is linear, scale linear, it's equal thing or not, you still have to sort of do a lot of processing per token. So it seems like, you know, not all characters are that important. So that's why I'm thinking about this, which is, hey, if you want to get rid of tokenizers, you probably want to do adaptive compute as well.
I guess what you just said is sort of highlighted as well by the current meta of just very aggressively filtering the training data, such that you really get the most intelligence out of your flops. And then in the next step, it would be to build this somewhat into the architecture, I guess. Yeah, very exciting about this direction as well. Thank you.
Yeah, all right, that's a great question. Thanks.
So one question regarding the efficiency and how to use compute to get wisely. So how do you see the field progressing for subquadratic-time architectures? Like, what do you see more promising, working on that, replacing the self-attention, or do you see promising the work on replacing like dense matrices with something as monarch matrices?
Right. Yeah. So far I've sort of talked about the attention layer, and like you can replace them with these, you know, subquadratic alternatives. I think as of right now, sort of short-term hybrid architecture, I'm pretty convinced hybrid architectures are the way to go, which is they are, I think in terms of quality, slightly better than pure transformer. And in terms of speed, they're also better, especially for long context. You're right, for some context length, you know, most of the time is spent in these MLP. And I think you kind of have to do both. Again, is this Amdahl's law, which is if you know, speed up one part of the model and you don't speed up the other part, then you don't get as much speed up, right? You know, you can speed up attention by 10x, but the MLP still accounts for, I don't know, 50 or 70% of the flop. So overall, end to end, you're not seeing that much speed up. And similarly for MLP, if you sparsify or quantize or compress the matrices in a certain way, and you leave the attention intact, you won't see that much gains. So I think people have been working on both, and I think that's the right thing to do. Personally, I also work on both sort of the attention layer and the MLP layer.
Thank you for the answer. I think that is all from the questions. We've got one more.
Hi, thanks for the talk. I was wondering, for FlashAttention 3, we got this new level of improvement thanks to the new instruction set and the tensor memory accelerator thing. But for the next generation of GPUs, are we expecting such a big change, or the paradigm, let's say, will remain the same?
Right. So I don't have specific information on next generation Blackwell. From what is public, you know, one of the things they're changing is sort of this blockwise scaling. So where the new Tensor Core is able to do blockwise scaling. So the answer is honestly, I don't know. Though from conversation with folks, I think I would expect sort of the optimized version of attention on Blackwell to come out quite a bit sooner than how long it took us to come out with FlashAttention 3 for two reasons. One is maybe the hardware is like sort of the the programming model is not changing as much. So, it's still asynchronous. Maybe there'll be more asynchrony, but it's not changing as much compared to going from MP to Hopper. And two, I think attention now is important enough that maybe there will be sort of first-party support, or NVIDIA sort of investing in supporting it, getting it out early. Yeah, the answer is I don't know how much difference it will be, but hopefully we'll get sort of an optimized version of attention for Blackwell pretty soon after Blackwell release.